Let's now take a look at how to represent the description of motion that we've discussed earlier on a graph space. So our focus will be to represent the motion of a body on a graph. The descriptions we can use for a moving body. How do we represent all these on a graph sheet? The second objectives will be to be able to interpret the motion of a body when its motion graph have been given to you. You should be able to interpret the motion of a body when it is represented graphically. Then finally, you solve simple motion graph problems. Let's now take a look at this scenario. Indeed, what we are going to do is the first type of motion graph, which is the distance time graph. We have two particles at rest here. They are about to move along this line, and we have a meter rule to measure the distances that they will be traveling for the time that this one will be recording. So the first situation is that they are at the reference point, which is at 0. The reference point is the start point, and the two bodies are at 0. The unit for the measurement of the length will be millimeters. Indeed, many of the calculations you'll be doing will be in meters, but this is a small experiment that we're doing, so we are using the millimeters. The time will also be in seconds. So let's see. This graph here will record or will represent how their motion will look like. So after 1 second, the blue particle moves to 7 millimeters and the red particle moves to 11 millimeters. Now on the table you can see the recording millimeters. Now let's come to the graph here. The graph has the time axis horizontally, and then we have the distance to be on the vertical axis here. So after 1 second, what will be the distances of the particles from their original position? The blue one has moved 7. You can read from here. We have the 0 point, and it has moved 7 millimeters, and that's where we put the point. Then the red one would have moved 11 millimeters, and that's where we put the point. That's for the first 1 second. Let's see what happens in the second. It's 2 seconds later from the beginning of the motion. Now, after 2 seconds, the second particle has moved to 14 millimeters position, and the red one has moved to 22 millimeter position, which means that the blue one is moving 7 millimeters every second, and the red one is moving 11 millimeters every second. So the time is 2 seconds later. See what happens. Now this was the position of the particles during the first second. It was 7 here and 11 here. Now after the second, or when the time is 2 seconds, we have the blue particle moving to 40 millimeters from the origin. You see, this 40 millimeters is from the origin. This is the origin. So the particles are traveling along this axis. But with respect to this time. So we have the blue particle at 40 millimeters from the origin, and the red particle at 22 millimeters from the origin. And this continues. So we move on to the next one, and the next one, the particles keep on moving until they get to the last point. So let's go through the motion again. Now I'm not going to talk, just see how the whole thing goes. There you are. So we can track the motion of the particles with time. We can record them on a table, and we can also represent them on a graph. And you can see the real motion up here. You see, so the particles were moving. Indeed, you can see clearly that the red was faster than the blue. That's why it is further away than the blue particle. Now, all these we've plotted will better be represented by a straight line, a linear graph. You can see the points; they are almost in a line. So instead of putting there the dot, we better represent them on a straight line. So we can now see the particles at various points all together. So initially blue was here, the blue came here, came to this side. You can see the interval, it was 7, 7, 7, 7 millimeters, 7 millimeters. That while the red was the first 1 second, it was about 11, then 11 interval, then 11 interval, and then 11 interval. You can see that. Alright. So there are a few things we would like to draw your attentions to. The motion graph here, you can simply do it without putting the dots there. So here we are. So this one represents the motion of the red particle, and this one represents the motion of the blue particle. They all started from the origin, and the distance from the origin kept on increasing until we got to the maximum distance for the blue and for the red within the same time period, which is 6 seconds. Now we can conclude that the red particle was moving faster than the blue. So the red particle moving faster, how do we see that on the graph? You can see clearly that the gradient of the graph for the red particle is much steeper. The gradient is higher for the red particle than the blue particle. So the steeper it becomes, the more gradient, the greater the gradient, you see. And the gentle it becomes, the lesser the gradient. Is that okay? So clearly you can see that this gradient is lower than the gradient for the red particle. So it shows clearly that the red particle was moving faster. So we use the gradient to indicate that the particle is moving faster or slower. That is for the distance time graph. So let's summarize for the distance time graph before we move on to the speed time graph. So the distance for from the reference point or the origin is plotted on the vertical axis, while the time taken to move to individual points are also plotted on the horizontal axis. I told you that the gradient will represent the speed of the particle. The greater the gradient, the greater the speed. And the y-intercept, I did not tell you, represent the initial position of the particle. And if you go back to the graph, the initial position was 0. That's at the origin. It could happen that at the time we started the clock, the particle could be somewhere. We start from there. In that case, on the graph, you have to start somewhere here, according to the reading. Alright. Now, if we have a graph, how do we calculate the gradient? If you don't know anything, then you just have to take 2 points, one point here and another point somewhere here, and see the vertical increase and the horizontal increase. So the vertical increase divided by the horizontal increase will give you the gradient. You can do that from your mathematics set. I hope you can do it so easily. So now let's have 2 examples and we have a motion graph here and we need to describe it. In fact, the same graph space is occupying the graph curves for 3 particles A, B, C. So particles A, B, C are traveling on a straight line and their motion graphs are shown on this graph. So how do we describe the motion of these 3 particles? I want you to try to discuss some of these on the platform, the origin. So after a second, 2 seconds, 3 seconds, the particle A started moving away from the origin. But there is plot for the motion of particle A. It doesn't look straight. It looks like a curve. So the motion, we can say, is not uniform. In other words, it is increasing in speed. So it is going away from the origin, but it is also increasing in speed. That is what is represented by the curved nature of the plot for the particle A. Now we go to particle B. That one is just as we saw in the previous simulation for particle C. 1 second, it is about 5 centimeters or 5 millimeters from the origin. 2 seconds, the same 5 millimeters from the origin. 3 seconds, the same 5 millimeters from the origin. What does it tell you? What's a simple way of describing this type of motion to a class 1 pupil? There's a term that we often use when we are describing this. Share your view on the platform and let's see how it goes. Let's look at the second example. We have another distance time graph. We are going to describe the motion on the graph and calculate the speed wherever applicable. The displacement or the distance is measured in meters and the time is also measured in seconds. So this is for the graph. At the beginning of time, when we have time 0, the particle was already at a distance from the origin. It was 30 meters away from the origin. After 20 seconds, it was still at 30 meters away from the origin. What does it tell you? Just a simple word. Then after about 50 seconds, it started moving. It started moving and we can see that one in the gradient. You see, so this, we have a gradient, a straight line gradient from 58 seconds onwards, and it continued until the 100th second. And when we go to the 100th second, by that time it was about 70 meters away from the origin. Then 10 seconds later it was still there. 20 seconds later it was still at 70. 140 seconds later it was still at 70. So you can describe this one quite easily. Yeah. Now the second question says calculate the speed wherever applicable. I don't want to say much about these two flat positions. Just tell me what they are and tell me whether we can determine the speed for the particle at these portions of the distance time graph. But I want to show you how to calculate the gradient for this portion of the graph. Now I can take this triangle, a point here and a point here, and the point here will be 170 and the point here will also be 50, 30. So the gradient will be to find the vertical change, vertical increment or the vertical change. That will be 70 minus 30 here. That gives me 40 for the numerator. That's for the vertical axis. We have 40. The change will be 40. Divided by 100 minus 50. That is 50. So 40 divided by 50 gives us 0.8 meters per second. That will be the gradient. And it will represent the speed. On a distance time graph, the gradient for any portion of it will represent the speed. Somebody could have taken the point here and the point here to calculate the gradient, and he should get the same thing because it's a uniform motion along this path. Alright, so I want you to try this question yourself and then share what you're able to do on the WhatsApp platform. Just read it and then do sheet of paper, take a shot, and then share. Let other people see